In this video, we'll look at torque and rotational motion. There are three words I want you to listen for in this video: torque, pivot point, and static equilibrium. Torque is a measurement of the ability of a force to rotate an object around some axis. So let's take a minute and think about a door. A door has a hinge, and in this case, the hinge is the pivot point. And depending on where you push or pull on the door, you'll get faster rotation. So if I pull or push on the door close to the pivot point, close to the hinge, I won't get much rotation. If I push or pull toward the center of the door, I'll get more rotation, and that's indicated by this swoop here. And if I push or pull at the end of the door, that will get the biggest change in rotation for the door. You can think of that. You also want to think about the directionality. So that was the position on the door. Now let's think about direction. If I pull parallel to the door itself, I won't get any motion. If I pull partly parallel to the door and partly away from the door, I'll get some movement from the door. And again, if I pull on the doorknob perpendicular to the door, I will get the most motion. So the definition of torque in AP Physics C is the Greek letter tau, represents torque, capital Greek letter tau, and it's equal to the force times R, which is sometimes called the lever arm, times the sine of theta. Going back to these examples, the red arrows represent the force, and the lever arm is the distance between the hinge and that force. So that distance there is R. That distance there is R. The torque is maximized at 90 degrees, and just a reminder that the sine of 90 degrees is 1. So that's what we would need to do to maximize the torque. The pivot point is relatively stationary. In an ideal situation, the pivot point itself would be stationary. Force and lever arm, the direction between them matters. So if I've got a central point here, I've got an R distance and then a force acting. In this case that I just drew, F and R are parallel. The angle between them is 0 degrees. The sine of 0 degrees is 0. So the torque created in this scenario is also 0. Now let's see what happens. Oops. Trying to autocorrect my circle. There we go. Now let's see what happens if I have a lever arm and a force acting perpendicular to that lever arm, like this. That's going to give me my maximum torque because the sine of 90 degrees is 1. Now, it's also true that I could have a scenario somewhere in the middle. So here's my pivot, here's my lever arm, and I could apply a torque at some kind of angle. And if I were to do that, only the perpendicular component of the force really creates a rotation. Okay. Torque is a vector, and it's actually a cross product. If you go look up cross product on the equation sheet, you'll see that vector A crossed with vector B is equal to A times B times the sine of the angle. And with torque, we can see why this makes sense, because it's only a component, only the perpendicular component that makes this work, or only makes it twist. What we're going to see is that the directionality of torque is actually into a third dimension. If I turn something clockwise, that's known as a negative torque. And if you think about, if I were to apply a torque to, say, a screw, let's pretend that's a screw, and I take a screwdriver and I turn the screwdriver, the screw will go into the wall. So I actually have three dimensions here. The center of the screw would be the pivot. The lever arm would be the distance from the center of the screw to the outside of the screwdriver handle. The force would be perpendicular. So the lever arm and the force are perpendicular to each other, and the direction of the torque would be into the wall. An X indicates the direction of into the wall. For a counterclockwise, torque, that's positive. And if I were to take and turn the screw to the left, it would come out of the wall. So I don't know if you've ever heard of righty-tighty, lefty-loosey, but turning it to the right's going to make it go into the wall, and turning it to the left's going to make it come out of the wall. And the torque vector coming out of the wall we would represent with a dot, like an arrow coming at you. Let's do an example. The length of a bicycle pedal arm is 0.152 meters, and a downward force of 111 newtons is applied by the foot. What's the magnitude of the torque about the pivot point when the angle between the arm and vertical is? And by arm here we mean lever arm. So here's our gear. Here's part of the pedal. Here's the other part of the pedal. And the person's foot is up here, applying force. We know that this lever arm, this is R is 0.152. And typically when we ride a bike, the force is straight down like that, and we know that that force is 111 newtons. And we want to know how much torque there is when this angle is 30 degrees. So I would use the torque equation. Torque is equal to FR sine theta. So that's 111 times 0.152. This is Newton meters. And then times the sine of 30. And that gives me 8.44 Newton meters. Now this is not the same thing as a joule. Because we're not measuring energy here, we're measuring the ability to turn something. So in physics, you also have to know the situation. This is not a work situation, not a linear work situation. It's a rotational situation. The direction here is clockwise, and we would need to label that because torque is a vector, so we have to give that direction. Let's do the same thing for 90 degrees. The torque would be equal to 111 newtons times 0.152 meters times the sine of 90. And when I plug that into my calculator, I get 16.9 Newton meters. That's the maximum value. And let's do it one more time for 180 degrees, 111 newtons times 0.152 meters times the sine of 180. Sine of 180 is 0, so that gives me 0 torque. This, by the way, would be when your pedal is at the bottom, when your foot's at the bottom of the pedal rotation. Okay, next, let's apply this to something we already know a little bit about, and that's static equilibrium. So one thing we learned from Newton's laws is that when the sum of the forces on an object is 0, there's no acceleration. This is for a linear situation. Now we want to start to investigate rotating situations, and it turns out we have an analogous rule. When the sum of the torques is 0, we have no rotational acceleration. If an object is in static and equilibrium, the analysis of any pivot point will show a net torque of 0. Let's try another example. A 40-kilogram child and a 30-kilogram child sit at either end of a 2-meter seesaw. Where along the seesaw should the pivot point be located to produce rotational equilibrium? I'm going to make a sketch here. Here's my seesaw. The seesaw is 2 meters long. I don't know these dimensions, but I do know that if one side, if I call the distance to the pivot point x, then the other side I would call 2 minus x, and I'll be using that later. Then I've got 2 kids on this seesaw. One has a mass of 40 kilograms, and the other has a mass of 30 kilograms. And those masses cause weight. So I could calculate the force of gravity on each kid by taking the mass times 9.81. And that's what I'm going to do. So I want to make sure that the sum of the torques is 0. So the sum of the torques would be the torque from the 40-kilogram child. The 40-kilogram child is making this rotate counterclockwise, so that's a positive torque. And the 30-kilogram child is going to make this rotate clockwise, which is a negative torque. So I can write that the torque caused by the first child is the force or weight of the first child times the distance from the pivot, which is x. So again, I'm doing force. Force is mg, and distance is x. And in this case, the angle is 90 degrees. So I'm not going to bother to write the sine of 90 because the sine of 90 is 1. And then the 30-kilogram child has a negative torque, so I'm going to, put a negative. Maybe I could just write negative right off the bat here. Maybe I could just say subtract. And this is a 30-kilogram child times 9.81, and the distance is 2 minus x. And that has to sum to 0. So now it's an algebra problem. You may notice that the 9.81s you can factor out and cancel. So I have 40x minus 30 times 2 minus x equals 0. I'll come up here where I have more room. So I can say 40x equals 60 minus 30x. I move that to the other side. Get the, add 30x both sides. I get 70x equals 60. So x equals 6/7, x is 0.857 meters. So this distance is 0.857 meters. All right, let's try this next example. A 65 kilogram woman is horizontal in a push-up position. What is the vertical force acting on her hands? So they helpfully tell us here where her center of mass is on her body. So we're going to assume that that 65 kilograms acts right at that center of mass. And that weight would be 65 times 9.81. Now in these torque problems, you can put the pivot point anywhere you want. And I'm going to put it at her toes, so I don't have to worry about the force on her toes, because the torque there would be 0. That just leaves me with her hands. Her hands must be producing a torque in the opposite direction. You may wonder why I did example 2 the way that I did. I was being very exacting. Maybe we can skip a step and say that the torque from her hands has to cancel out the torque from her center of mass. So torque from the hands has to be equal and opposite from the torque from the center of mass. So the torque from her hands is the force she's exerting with her hands times the lever arm. And the lever arm is 1.5 meters because that's the distance from her hands to her toes. And then the center of mass, 65 times 9.81 is the force, and that distance is 1 meter. And when I solve that, I get that the unknown force is 425 newtons, and the direction would be up. I know that by looking at the diagram. Okay, what is the vertical force acting on her feet? Well, she has to be in static equilibrium. So one way to solve this is to say that her feet must be holding her up. So now if I don't think about the rotation of her, if I just think about her having 425 newtons up and 65 times 9.81 newtons down, whatever force is on her feet must balance out the downward force. So 425 plus the foot force is going to have to equal 65 times 9.81. I don't have my calculator handy, so I hope you're okay if I use 650. And the foot force turns out to be 225 newtons. All right, thanks for watching, and good luck with your first assignment. I'll see you soon.